So as a bonus, let's actually look at the proof of the squeeze theorem. This is for folks who have seen epsilons and deltas, in other words, the rigorous definition of the limit of a function. For example, the videos that I've made pretty recently about the careful definition of the limit of a function. So let's look at our assumptions. We're assuming that we have three functions. F of x is less than or equal to g of x is less than or equal to h of x. I've just been saying for all x near, this is a? No, it's x. No. For all x near a, we need to make that a little more precise. So that means there's some fixed positive b that gives us the window around a, so it's everything from a minus b to a plus b, where this is true. Okay, and b is going to come in a very minor way into the proof. And we are assuming that the two outer functions have known limits and those limits are equal. That's really crucial. Okay, to show is that the limit as x goes to a of g of x is 0 as well. Okay, so almost every sort of basic limit proof like this starts with the same sentence: let epsilon greater than 0. We want to show, that's our error tolerance for g. We want to show that g can be made within epsilon of L if you make x sufficiently close to a. And then we just have to figure out sufficiently close. Okay, well, but this let epsilon greater than 0, not only is it what we have to start with to prove what we want to show, it activates the limit statements about f and h. Once we've said this, there is some delta 1 greater than 0, such that for all x with x, the absolute value of x minus a is less than delta 1, absolute value of f of x minus L is less than epsilon. So when x is close to a to a certain degree, which depends on the function f, then f of x is close to L. And there's some quite possibly different delta. We can't assume these deltas are the same at the start, such that when x is within delta 2 of a, h of x is also within that same epsilon of L. Okay, and h might be like something that just is much more reluctant to have a limit, and that relationship of delta 2 to epsilon might be much different from the relationship of delta 1 to epsilon. But the cool thing is we just need to show there's some delta. It has to be greater than 0. We just need to know there's some delta that works, that activates both these statements at once. And this is really about just logic and just very basic inequalities. If I take a delta that's smaller than both of these guys, but still positive, both these statements will be active at once. I'll have satisfied the f and h criteria for smallness, for closeness of x to a. There's a really easy way to do that. Just take the minimum of the positive number delta 1 and the positive number delta 2. The minimum of two positive positive numbers, is still a positive number. So almost we're going to say let delta be the minimum of delta 1 and delta 2. Now, technically, these could be so easy, f and h could be so easy to take limits of, that we might accidentally have at some point, for some epsilon, we might accidentally have some delta 1 or delta 2 that's actually outside the b range. And so we actually don't even know this relationship between f and g. But we know that eventually that's true, as long as we get within b of a as well. So let's just throw that into the mix. So let's just make sure basically that delta is something that's at least as small as delta 1, at least as small as delta 2, and at least as small as b, so that everything we want to be true is satisfied at once. So in other words, let's just take the minimum of those three things. Minimum of 3 positive numbers, still a positive number. Pretty basic. Okay, so when x is delta close to a, then we can say that this statement is true. And I've gone ahead and broken that out, because here it really is really helpful to break it out in this style without absolute values. F of x is between L minus epsilon and L plus epsilon. H of x is also between L minus epsilon and L plus epsilon. And we have this really important relationship that g is between f and h. Now it's just combining some inequalities. Because L minus epsilon is less than f, and f is less than g, well, that means L minus epsilon is less than g. It's the transitive property of inequalities, of less than. And because h of x is less than L plus epsilon, and g is smaller than h, g is also smaller than L plus epsilon. Guess what? That's what we need to show. If you like the absolute value style, it's not really a different statement, but you'll see it more often in this way. The distance between g of x and L is less than epsilon. So if you just sum up, just take out the middle stuff of the justification, what we see is for all x, with x minus a is less than this positive delta, then g of x minus L is less than epsilon. And epsilon was totally arbitrary at the start, and we showed a way to find some delta. We don't know any of the details of delta, but we know it exists. That's the key. There is some delta that makes this work. That's the definition of the limit as x goes to a if g of x is equal to L. This is a nice one because it's very elegant. As I said at the start of the first video, there's nothing really algebraic that necessarily needs to be true about limits. When you look at the proof of a lot of limit laws, they combine limits in algebra, and so you might see some algebraic funkiness. And especially if you're doing sort of finicky examples of like x squared plus 3x, things like that, it looks like you have to do a bunch of algebraic trickery. This is really about inequalities. It's just about logic and greater than or less than. There's really nothing else going on here. In fact, there's something a little subtle I want to point out. We actually never used this one. We never used that f of x was small. The point is that f of x is the lower bound for g. We want to show that that's coming up and squeezing from the bottom. So we want to show that f of x is big. That's why we use this inequality. And h of x was the thing that's squeezing g from the top. We want to show that that's small so that they get squeezed together. We actually never used the full strength of our assumption about f and h. That means that there's a better theorem lurking here. I won't mention the details, but it turns out that because we didn't use those, there's sort of one-sided notions, and it's different from the usual one-sided notion of like as x goes to 0 minus or 0 plus, like from the left to right. There's a different kind of one-sidedness in terms of the output values for a limit, and it's called lim sup, the limit superior, and the lim inf, the limit inferior. And you see those a lot, usually in a more like advanced calculus context where you really prove everything. But while I was doing the video, I was noticing, oh yeah, this is really a weaker version of a tighter result that would use those notions of lim sup and lim inf. So you can look those up if you are curious.